Unless x approach a certain number, that is the limit to a point, and sometimes the result was that y became arbitrarily large. That is, we ended up with a vertical asymptote. In this section, we're going to let x get large and see what happens to y. So in this section, we are looking at limits to infinity. And of course, you can approach negative infinity heading to the left or positive infinity heading to the right. So we're going to just take a function that we've looked at probably in the past and look at what would happen if x got infinitely large with this particular function. And then we'll talk a little bit about the intuition of it. Okay, so here's our function f at x, and we want to know what is the limit as x approaches infinity for this function, x squared minus 1, all divided by bracket x squared plus 1. So we're going to do some numerical analysis to begin with. Then we'll look at different strategies for approaching that, and then we won't come back to this numerical analysis again. We will do it algebraically. Okay, so just keep in mind when you're doing numerical analysis, you're looking for a trend, but you actually haven't proved anything. A proof comes algebraically. It doesn't come from 1,000 examples. You get an intuition about it, but you haven't actually proved it. Okay, so what happens if x were to be, so let's go to infinity. So we're going to start at 0, and then I'm going to get something bigger like 10, and something bigger like 100, because I'm letting x go to infinity, in this case positive infinity. And then let's say 1,000. So you go ahead and grab your calculators, and I'll do the first one for you. If x is 0 in my head, I could just say that I'm -1 here. If x is 10, 10 squared minus 1, 9 over 10 squared plus 1, 101. If x is 100, I'm going to get 10,000 minus 1, which would be 9,999 over 10,001. You guys can give me your approximation of what you're getting for this. You have your calculators?
Decimal 9802.
Thank you. And this one?
Decimal 9998.
And how about you do 1,000 squared minus 1,000 squared plus 1? What are you getting?
1.
Okay, and if you highlight that, I bet you're not getting 1. I bet there's there 0.999999999. It is, isn't it? Okay, as x is approaching infinity, what do you think y is getting closer to? It's like to 1. The way you would write it is the limit as x approaches this function x squared minus 1 over squared plus 1. That limit is equal to 1. If you were to graph it, then you know that you would get a horizontal asymptote at 1. Equals 1. And we can see that x y -1, so I've got that point on there. And my function comes up to this horizontal asymptote. Wait, do you recognize that that function isn't even?
Plus
That function negative x would be the same as the function at x. Even function, so because I know it's even, I actually do the work of looking at the limit to negative infinity. The exact same answer because an even function reflects x. looks the same on both sides. Okay, that doesn't always to horizontal asymptotes. So when you have a limit to infinity, is a horizontal asymptote. Always have a limit to infinity. Sometimes your function just keeps on getting bigger, and then you say it just increases without bound.
Because you just put what are the minimum point that the chart out made. After that, how did you know that's what the graph was?
Okay, so part of it is that graph, and then I'm actually not 100. What happens between here and here is that this function has to come up to its horizontal. So as it approaches infinity, 1. Okay, did it do something fun between there? Maybe. Zoom way out on your calculator, that's the shape you're gonna see. Okay, let's talk about this intuitively. Function x squared minus 1 over x squared plus 1. Infinity is. It's a number that's so big is because there's always something bigger. So if you, I can find one, I can add 1 to your number. So infinity, guess it doesn't really exist, but it does exist. Growing and growing and growing. So if we think about being really big numbers, let's think about money. If x was all the money and you shared it, and then you divided it by all the money Bill Gates had, and you gave him another $1. Can you see that that would be in hints at subtracting $1 and adding $1? He's gonna notice that you stole $1 out of his bank account. Okay, so at infinity, what's the only thing that matters here is that ratio of x squared over x. So you can kind of use pretty sloppy arithmetic when you're infinity. We're creating an age behavior model. If x is large and I take 1 away, that's kind of irrelevant. If x is infinitely large, add 2, it's kind of. What's relevant at infinity is I've got the same divided by the same number, so I'm going to get 1. Okay, so each limit as x approaches infinity equals L. The values of the function, that is the y value, become closer and closer to that as x becomes larger and larger. Along y equals L is the horizontal asymptote of the curve or function. If the limit is approaching infinity, L x infinity is negative L. And perhaps we're not used to this. You have 2 horizontal asymptotes. You can have one and one at positive infinity. Or you might have a function where the okay, and get this all together example here. So this and could you draw the -1 and 2 spaces, -3 and 1, 2, 3, and that's this thing by axis. Here's 1, here's 2. Right. So carefully draw this graph. This one here. So those two branches. And then here I'd like you to draw this. Okay, so we've got 3 branches for and to look at 2 different kinds of limits to and limits to infinity. I'm just going to try to keep the color organized to just help you visualize. So infinite limits and limits to infinity as which is infinity, positive, negative. Set infinity, which is infinity. It limits to a point. Give you infinity for an answer. So infinite limits are your possible vertical. So let's just make a note of vertical asymptotes. When you look at the limit approaches a function and you get positive or negative infinity. Okay, the limit to a point gives you infinity. We call that infinite. On the we get limits at infinity. So a horizontal asymptote we get horizontal asymptote. The limit as x approaches positive or negative for a function is equal to this limit. So your I calls this since you say over here I use these limits at infinity give you horizontal asymptotes. They don't necessarily limit to you infinity for where your vertical asymptote. So look at the diamond and for those 2. Okay, so let's start first with vertical asymptotes. The limit to a point is infinity. So limits. So then where do you see your side one right here? X equals negative 5. I see another one right here. X is equal to. So if we're looking at infinite, we are looking at our value. We have to look at what is as x approaches value of negative 1.5 from the left for this function, and what is the limit x approaches that value 0.5 from the right this function. Okay, so answer to that question. So permissible value negative 1.5. I approach from miles are going to positive. As I approach from the right, my values are positive. Kevin, so x isn't allowed to equal is limit approaches 2 and right. Okay, 2, the x value of 2 looks like are negative. I approach 2 from the right-hand side, I want to infinity. This or go vertical -1.5. And to our vertical asymptote at x equals x. And forecast from limits to infinity. So your behavior, your class notes if it exists, that you'd be looking at one limit for this function as go negative infinity, and its limit for this function as s goes to positive infinity. Okay, so we're gonna look at it goes so x values infinitely getting closer to, it looks like getting closer to this line will each right here, and we go to negative infinity is equal to is positive. It's this line. What's this line? Well, like equals. So we're in the outs. It is equal to 2.5.